Ready? Okay. So the first thing I would write is this. This equals, that's correct, this. But the next does not equal. The next is approximation of this. I should write dy, but I will write the definition. Three things I have to identify. What is the function, which is the cube root of x? Good. The cube root of x. Good. X is 1000. Very good. And dx will be? Very good. So all I have to do is from here find f prime of x, which will be 1/3 x to 2/3 x to negative 2/3, which is the cube root of x squared. Right? Bring down the power. Right? Do you need me to read that, to write that? Okay, so the cube root of x is x to 1/3. When we differentiate x to 1/3, x to 1/3 prime, we have 1/3 x to negative 2/3, which changes into this, the cube root of x squared. So that's how we get that. That's the f prime. So now here I can write the equal symbol because this piece equals this. It's just that that does not equal this. So f of x will be the cube root of 1000 plus f prime of 1000 will be this with 1000 in it, the cube root of 1000 squared, and then the x is multiplied by -1. That's all I need to do. I can take the cube root from this because it's 10 times 10. I can take the cube root from this, which is 10. So plus, oh, I should have written minus, but I'm going to do it. So this is 10 times 10, 100 times 3, 300. So 10 minus 1 over 300. 3000 minus 1, 2999 over 300. Any questions on this? Any questions? Okay, you can approximate and check the answers. Now, Ricky, are you finished?
No.
Okay.
Yeah, I'm gonna go over this right now.
Yes, I'm going to go over this right now. Okay, so let's take a look at the other one. So for this one, we have 1 divided by the square root of 401, which we know this is f of x plus dx. But we know that this is approximately f of x plus f prime of x dx. We have to identify three pieces, f, x, and dx. Can anyone give us f of x?
1 over f the square root of x.
Yes, which I will immediately change into x to -1/2. Can anyone give us x?
100.
Excellent. Can anyone identify dx?
1.
Very good. So I have to find f prime of x, which will be -1/2 times x to -1/2 minus 1, which is -3/2. So this will become -1 over 2, the square root of x cubed. You can simplify it or not, it doesn't matter at this point. Now this will be equal for sure. These two sides are not equal, but this equals that. F of 400, it's 1 over 20 plus, I should write minus, 1 over 2, the square root of 400 cubed. and times dx, which is 1. So this will be 1 over 20 minus the square root of 400 is 20, but 3 times. 1 times 2 times 20 times 20 times 20. Or just write 20 to the third, of course. Times 1, there is no need. So 1 over 20 minus 1 over, this is 16 with 3 zeros. So the least common denominator is 16,000. And I have, what, 800 here? Minus 1, 799. Again, you can approximate to check. I don't really care if you do or not. But you should, because you want to make sure that it's the same thing. Any questions for me? Yes, please.
Where's the negative 1 over 2 x squared of x coming from?
Say it again.
The negative 1 over 2.
When I differentiate x to any power, I bring the power down and I subtract 1 from the power. I bring the power down, negative 1/2, and I subtract 1 from negative 1/2 to get negative 3/2. Is that okay?
Yeah. I just don't get how it becomes 1 over 2.
Here?
Yeah.
Because it's a negative power. The negative power brings the quantity to the denominator.
Okay.
X to negative 3/2 is 1 over x to 3/2, but I already changed it into a radical.
Okay.
Better? Other questions here? Anyone? Anyone? Other questions? Yes, please.
I don't mind simplifying it. Just
Say that again.
I don't simplify the whole thing.
How we found it?
Yeah, I just put that line. I don't like.
This one?
No. I
This-
just finish it now. That line. Oh, yeah. 1 over 20. No, yeah, I just put that line and then no. That line. 1 over 20. Which was the bottom. Yeah, that one. I just put that one and I don't like simplify that.
So you're saying that on your paper you didn't continue. That was the final? Yeah, but we still need to see the yeah. But you're on the right track. That's fine. I see. But we have to use algebra or basically arithmetic to show what that is. Okay. Anything else here? We have one more little piece from 3.10, and then we'll look at 3.11. So let's go back to our graph. Of course, this is f of x. Of course, this is p with x, and what is the y value? Excellent. F of x indeed. Okay. So this time we're going to say that this is at a particular x. So I'm going to say x is a. It doesn't matter really. Okay, we're going to look at both situations. Here is the tangent line to P. Can anyone give us the slope of this line? Very good. This is indeed f prime of x. In this case, if we want to say that x is a, you can also say that this is f prime of a. Very good. Excellent. I would like to determine the equation of the tangent at P. Equation of tangent at P. What do we use to find the equation of the tangent line at P? Yes, excellent. Y minus y1 equals the slope times x minus x1. We have the slope, f prime of x. We have the point, x, f of x. So then, I replace. See if you have any questions so far. So the point is x comma f of x. We're going to write it again with a. I want to show both. So the point is x1 comma y1, and the slope is f prime of x. So y minus f of x equals f prime of x, x minus, I'm getting into a situation here, so I have no choice. I have to change that into a. Because I can have x minus x. So x, we have to use a in this particular situation. We can write the linearization in a minute with both, but in this case, I'm running into x minus x. So this is f prime of a, this is f prime of a, this is f of a, and this is a. So then f of a, y minus f of a equals f prime of a, x minus a. So finally, the equation will be f prime of a times x minus f prime of a times a plus f of a, because we move it to the other side. If we rearrange it to make it a little bit nicer, like y equals f of a plus f prime of a times x minus a without distributing, this is the equation of the line that is tangent to P. Now, here's my next question for you, and you'll tell me if that's acceptable. See, this line is tangent to the graph in one point, and one point only, of course. Now, if a, let's say a is 4, and I would like to estimate this function very, very close to a, like, for example, as we just did, 4.001, or on this side, 3.999. Do you think that these two, the function and the equation of the tangent line, will be in value very, very close? Would you agree? Okay. What about another point here? If I create the tangent, I draw the tangent, of course, for a different a value, or let's say for 10. If I need to estimate this function close to 10, tiny, tiny to the left and to the right, if I use the equation of the line, which is the equation of the tangent line, or I use the original function, I'm not saying it's going to be the same. Will they be close?
Yes.
Yes. So here is our conclusion so far. Very good. Any function, of course, it has to be differentiable, right? Any function can be approximated by or with, if you want, a line near any p of a f of a. But it has to be near. We say on an open interval close, near any point. So any function can be approximated by this for any point a comma f of a. Notice that I did not put the equal symbol. F of a plus f prime of a times x minus a. So this is, one more time, this is called the linear approximation of f of x near x equals a. Yes, Ricky, go ahead, please. Yes. We also have something that is called the linearization, but this equals the linearization of f of x near a. What will that be? The same thing. F of a plus f prime of a times x minus a. So what is this concept all about? It only says that a function can be approximated by a line at any point where it's differentiable. What would that be like? What line would that be? The equation of the tangent. So let's go back here one more time. So this is the equation, or this is the tangent line at P. The equation of this line or the function are extremely close in value near any particular point. I cannot use this equation of the tangent for this point, or vice versa, right? So if I'm close to x equals a, if I use the equation of the tangent, which will always be easier because it's going to be a linear function, or the function, I can evaluate, I will have an error, but not too big if I use the equation of the tangent line. That's all it means. So any function, when it's differentiable, of course, can be approximated with a line. Which line? The equation of the tangent line. L of x is the linearization of f of x near a. Any function at any point, if it's differentiable, can be approximated by a line. Which line? The equation of the tangent line. So let's pick a couple of problems to look at. On page 255, we can determine the linearization from 1 through 4. Pick a problem, anything you want, 1 through 4, on page 255. We can also consider problems 15 through 18 or 15 through 22, where we are asked to compare delta y to dy. But let's find the linearization or the linear approximation. They're asking for the linearization. Okay, I'll choose number 2. F of x equals sine x. A equals pi over 6. So they're asking us to find the linearization L of x. And you know that this is nothing else but the y value given by the equation of the tangent line. So f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So let's compare. This time a is pi over 6, so I have f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So I'm asked to find the line that approximates sine x near pi over 6. If I'm not too far from pi over 6, I can plug in sine, or I can plug in x in here. And I will find not an exact value, but pretty close. So let's continue with writing sine pi over 6. I know f prime is cosine, so plus cosine pi over 6 times x minus pi over 6. Let me refresh our memory on the trig function values. I think we did this before, but let's do it one more time. So we have sine and cosine. We have pi over 6, the smallest, pi over 4, the middle one, and pi over 3, the larger one. You do not need to memorize anything else but what I'm showing you here. Sine is 1/2, and so is cosine for pi over 3. Cosine for pi over 6 is the square root of 3 over 2, and so is sine for pi over 3. So these are reversed. And this is the only angle that has the same. Yes. That's really all you need to remember. So then sine pi over 6 is 1/2. Cosine pi over 6 is the square root of 3 over 2. And then x minus pi over 6. So unfortunately, we have to distribute. So this is the form in which we have to present it finally after we combine like terms. And these will be combined. This is the nicer form to remember. But this is what we really want at the end. And these in one number. So then I will have to distribute the square root of 3 over 2 and then add 1/2 to the whole thing. So this is the square root of 3 over 2 times x. plus 1/2 minus the square root of 3, pi in front, pi the square root of 3 over 12. So the square root of 3 over 2 times x is in front. I copied 1/2 next, and then I distributed the square root of 3 over 2 to pi over 6, and I got pi the square root of 3 over 12. So this becomes the square root of 3 over 2x, and this needs a 6. So plus 6 minus pi the square root of 3 over 12. And this is the line that approximates sine x near pi over 6. Any questions on this? Yes, Vanessa, please.
Oh, I kind of got lost before the final answer. I got lost.
Here? Yeah. So I copy the 1/2 after I distribute it to x. Then I have to distribute to this, and it's here. And these two numbers have to be in 1. Because this is mx plus b. Y equals mx plus b.
Wait, you added 1/2 plus root 3 over 2. Wait,
It's minus.
no, the first part.
Here.
No, before that, the first term.
So I have the square root of 3 over 2 times x, which is this part.
Yeah.
Then I wrote the 1/2.
Okay.
And then I distributed the square root of 3 over 2 to this, and I wrote it here.
Okay.
So because the least common denominator is 12, I have to multiply this by 6. I get 6 minus pi the square root of 3 over 12. Is that okay?
Yeah.
Because this has to be presented into mx plus b form. This is the slope, and this is the y-intercept. Is that better? Okay, let's do another. We need another for the linearization. Okay, so let's look at, let's say 4, x to 3/4 at 16. So 4, f of x equals x to 3/4 at a equals 16. Same page, 255. So we know that the linearization of this function will be the equation of the tangent line at the point x with a or x equals 16, which is f of 16 plus f prime of 16 times x minus 16. Are you with me? Is this okay? Yes? Okay, all I have to do is just find f prime. F prime of x is 3/4 x to negative 1/4. I would prefer writing it like this, but that's me. So then the linearization will be 16 raised to 3/4 plus 3 over 4, the 4th root of 16, times x minus 16. Now we have to simplify everything. What is the 4th root of 16? 4th root, just the 4th root. The 4th root of 16 is 2, but now 2 to the 3rd. Very good. So this is 8. How much is the 4th root of 16?
2
Times 4. So plus 3 over 8 times x minus 16. 3/8. Okay. I distribute, combine like terms, and present y equals mx plus b. So 8 plus 3/8x minus 6. So then the linearization is 3/8x plus 2, only near 16. I should have written the here before, or the previous example, just to make sure we understand. This, it was, okay, this is only near pi over 6. This equation will not approximate, will not work for any other point, but only near pi over 6. The same thing here. I can approximate this function using this function only if you're asking me to evaluate it near 16. If you say use this function and evaluate at 21, or 20.3, I will say I can't. It's too far. Does that make sense?
Where's the minus 6 coming from? Shouldn't it be minus
3 over 8 times x. 3 over 8 times 16. I simplify by 8. Negative 2 times 3. Negative 6. I have to distribute 3/8 to x and to negative 16. So 3 over 8 times 16 over 1. I get 3 times 2 is 6, but there is a minus. So from the very beginning, this is the linearization one more time till we get used to it. We have to repeat it, right? F of a plus f prime of a times x minus a. It's from y minus y1 equals the slope times x minus x1. That's the x minus x1. Better?
Yes.
Good. Yes?
Well, when we rewrote it,
Yes?
why are we putting 16 to the 3/4?
You mean here?
Yeah. No, right above that. To the
Because I
left.
have to differentiate. So when I differentiate, I get 3/4 x to negative 1/4.
Okay.
I bring down the power. I subtract 1 from the power. 3/4 minus 1/4 minus 1 is negative 1/4. Because the power is negative, I have to bring it to the denominator. So it's 3 over 4, the fourth root of x.
Okay.
Is that what your question? Was that the question? Did
No,
I
but
answer your
it's
question?
answered, yeah.
Okay, so then I have to plug in f prime, I have to plug in 16. It's this portion.
Okay.
So I plug in 16 in f prime. And then x minus 16 I just copied. And then I copied f of 16. 16 raised to 3/4. Is this better, everyone? We understand every step? Every step? Okay. Do we understand how we got to this? Do we understand that this is only near 16? Is that clear? Yes, please, Vanessa.
I understand it. I'm kind of confused. You gave us two formulas, like which you gave us the LX equals.
Very good. Yes, very good question. If we're asked the linearization, then we will write L of x equals. If we're asked the linear approximation, we will write the small f of x approximated. Very good question. Let's go back and clarify that one more time. So when we are asked to find the linearization, we will write the uppercase L. I should have mentioned that. Thank you. Uppercase L. If we're asked to find the linear approximation, they will write f of x approximately. Although the definitions are the same. Yes, Chris, go ahead. You want to say something? Oh, okay. Is that clear? So there are two different things. Although, however, it is the same formula.
How do we know? I don't expect that as a formula.
If we are asked to find the linear approximation, we will write this. If we're asked to find the linearization, we will write this.
That's all
That's all is
it's different.
different. Yes, that's all is different. Thank you for pointing that out. Okay, so let's illustrate also the difference between delta y and dy with any of these problems. So we can look at find the differential of each function, but that's just one piece. But this one has more, it's more involving. And I like that better, or this one, in which, let's read, find the differential and evaluate dy for the given values of x and dx. And this includes everything. Compute delta y, compute dy for the given values, then sketch a diagram we can. We already did. That's the same diagram we looked at before. And compare the two and show in the diagram delta y and dy. Let's choose from here, whatever you want. Any preference? 20, very good. So let's look at 20. 20 is y equals the square root of x on the same page. Y equals the square root of x. They are giving us x equals 1, and delta x and dx equals 1. Kind of a big dx. It's not small enough but we'll see what we get. So we're asked to find dy, and we're asked to find the delta y and dy. Let's start with the easiest. Which one is the easiest between delta y and dy?
I thought they were the same.
They are, yes, but in calculating them, one is more difficult than the other. Yes, they are close to each other. You're right. Delta y should be very close to dy as long as dx is not correct. But which of these two is easier to calculate? Always, because dy is f prime of x dx, and I'm done. Exactly. This one, you will see in a moment, requires way more work. Maybe not. It's a simple function, but more than this. Okay, how much is f prime of x? Perfect. So that's all I have to write. That this is 1 over 2 the square root of x dx, and I plug in 1, I plug in 1, and I got 1/2. There is nothing else. Now, let's determine delta y. And remember what delta y is. F of x plus dx minus f of x. So how much is x plus dx?
X plus 1.
I mean, but x is 1. Right. So f of 2 minus f of 1. F of 2. The square root of 2. Don't be bothered by that. I forgot to turn off my phone. I'm sorry. Minus 1. This is the exact. This is the exact answer. However, if you punch it in the graphing calculator, we will have the square root of 2 minus 1 versus 0.5. As you see, as expected, because dx is not tiny, and because x is also small, 0.5 and 0.41, they're not pretty close. They are, but not pretty close, right? It depends on dx. That's all we needed to do. So delta y is, as we know, the exact change in y for a 1 change in x. dy, which is 0.5, in this case is an overestimate, right? This is 0.5 and this was 0.4. Let me write it, approximately 0.4142, and this is 0.5. This is the exact change in y, in error of the area, in error of radius, and any other word problem. So the exact change is 0.4142, and the approximation is 0.5 using differentials. Using the derivative, the approximation is 0.5. Not using the derivative and determining the exact difference, we get 0.4142. Yes, Vanessa, please.
Where did you get the formula for delta y?
These two?
Yeah, no, the second
Okay.
formula.
Yes, let's do that again. So when we looked at Tuesday, so for a small change in x, we have, this is f of x, and for a small change in x, this would be f of x plus dx. This is the exact change in the y values for a small change, for the dx change in x. This is delta y. F of x plus dx minus f of x. That's the exact change. Okay, from last time.
Yeah.
And here, this is the differential. So in our example, this will be 0.5, and this will be 0.41. Better?
Yeah.
Perfect. Can we consider this section done? Would you like to practice more?
Yes.
Good. Let's look at a word problem. We looked at the, what was it? We looked at the radius. Yes. Let's choose another. Yes. Let's look at 33. On the same page, 255. Good example. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1. Let's stop and identify what is given here. So what is 30 centimeters and what is 0.1 centimeter? No, we haven't differentiated yet. Yes. So that's the x, and very good. X is 30 with a possible error in measurement of 0.1. Excellent. Use differentials to estimate the maximum possible error, the relative error, and percentage error in computing the volume of the cube. So in part A, for the volume, and in part B, for the area. Part B, and the surface area of the cube. Very good. So it says one more time, use differentials to estimate. Don't find the exact. Use differentials to estimate the maximum. So what am I asked to determine? Am I asked to determine this, or am I asked to determine this? I'm asked to determine this. Very good. But this time for what? For the volume. Good. So let's determine this is a cube. Let's determine the volume of a cube. The volume of a cube is? Good. So it's x cubed indeed. Excellent. So you told me already that we are asked to find what again? For the volume. We're asked to find dy, but this time is dv. Very good. It is dy. Perfect. But we use the notation volume. Perfect. So let's determine this. How much is dv? 3x squared times. Very good. Remember one more time. dy equals f prime of x dx. The volume depends on x. I differentiate 3x squared dx. Good. So all I have to do is punch it in. So it's 3 multiplied by 30 squared multiplied by 0.1. I will get a number. What is the measurement unit? Exactly. It has to be. We're talking about volume. So this is the estimated error. If there is a tiny error in the edge, this will trigger this error, approximated error, not exact error, in the volume. Caused by that dx, caused by 0.1. So how much did we get? 27. 27? Okay. Good. So this is the estimated error in volume. What is the relative error? Okay, I think you don't agree with what we get. So it's 900 multiplied by 3 and multiplied by 0.1. 270. Very good. Perfect. Relative error. The relative error is the error over the total. So dV divided by V will be the relative error in volume. So dV over V, I like to write it like this. dV was 3x squared dx divided by x cubed. You can say, why do you write the formula again? Ooh, we know already it's 270. Yeah, I like to write it like this because I like to simplify. And show that this is basically 3 times the relative error in the edge, the measure of the edge. So this is 3 times 0.1 divided by 30. So this is 0.1 divided by 10, which is 0.01. There is no measurement unit. Cubic centimeters over cubic centimeters, no measurement unit. And now we are also asked to determine the percent error. All we have to do is move the decimal digit 2 spots to the right. So the relative error in the measurement of the volume for a tiny error in the edge that triggers 270 centimeters cubed of error in the volume, which is 1% of the volume. So that's the error created, or 0.01. We're asked to do the same thing for the area. Ready? So what is the total or the surface area of the cube? What will you say? Part B, the area. Times how many? 6x squared. Very good. We want to determine the estimated error created by a minor error in the edge.